Let us now look at the next question of the IIT JEE 2017 advanced paper, and the question says, if for a real quantity alpha, if the system of equations given by this matrix multiplication here has infinite solutions, then we have to find the value of 1 plus alpha square. Well, note that in this case we have been given that the multiplication of these two matrices is equal to this column matrix having elements 1, minus 1 and 1. And we have three variables x, y and z here, and we also have a real quantity alpha which forms this matrix given here, and we have to find the value of 1 plus alpha square, for which this system of equations has infinitely many solutions. Now, note that whenever such a system of equations has infinite solution, then what we do is we realize that this matrix here, now the determinant formed by this matrix should be equal to 0. So, whenever we have such a situation in which we have such a matrix multiplication that has variables x, y and z, then such a matrix multiplication represents linear equations, and if that linear equation has infinite solution, then we can write the determinant formed by these elements is equal to 0. And so we will now check the determinant formed by these elements. So we write 1 alpha and alpha square in the first row. The second row has alpha, 1 and alpha, and the third row has alpha square, alpha and 1. Now note that here we have removed the matrix bracket and put a determinant bracket here. Now, because this is now a determinant, we will denote it by this symbol, and this becomes equal to 0 because this system has infinitely many solutions. Now, because this is equal to 0, we can now expand this determinant on the left hand side of this equation. So now expanding the determinant in the standard manner, we will get 1 into 1 minus alpha square minus this alpha multiplied by alpha into 1, that is alpha, minus alpha square into alpha, that is alpha cube. So I have a alpha cube here. Then I have a plus alpha square, and then the multipliers will be alpha into alpha minus alpha square into 1. So here I have a alpha into alpha, which becomes alpha square, and then I have a alpha square into 1, which is again alpha square. Now note that this third term here reduces to 0, and so the left hand side comes equal to 1 minus alpha square minus alpha square. So I have taken an alpha square out from here, and so this becomes an alpha square, and so what is left inside this bracket is 1 minus alpha square. And now this third bracket gives us a 0, and so this entire third term becomes 0, that is, it vanishes. And so now we have this kind of an equation, and this is equal to 0 because we had seen that whenever such a system has infinitely many solutions, we can equate this determinant to 0. So now note that because this is equal to 0, we can further write this here. So I will write it separately here. Now the same equation can be written as alpha to the power 4 minus 2 alpha to the power 2 plus 1 is equal to 0. So what I have done is I have just taken the alpha square terms together, and then I have taken alpha to the power 4 term together, and so I have obtained this expression, which is a quadratic in alpha square. Now, because this is a quadratic in alpha square, I can further write this as alpha square minus 1 the whole square is equal to 0. So in fact, this is a perfect square, and so because this is a perfect square which is equal to 0, we can now take the square root on both sides and get the final result as alpha square minus 1 therefore is equal to 0. What this means is, because alpha square minus 1 is equal to 0, we can now say that alpha is equal to plus or minus 1. So we have now obtained these two possible values of alpha, that is, alpha can be plus 1 or alpha can be minus 1. Now, let us check these two values and let us see what these two values give us further. Note that if we take the first case in which we assume alpha is equal to 1, so we write if alpha is equal to plus 1, then we will replace each of these by an alpha, and so we will now get, inside the matrix, we will get 1 alpha and alpha squared, which becomes 1, 1 and 1, because 1 square is 1. Now again, this other rows also become 1 each, so we have 1, 1, 1 everywhere inside this matrix. And now this is multiplying the column matrix having x, y and z as the entries, and this multiplication of matrices should be equal to 1, minus 1 and 1. And so here we have 1, minus 1 and 1. Now note that in this case, if we expand this and write it as 3 linear equations, then we will obtain 2 different expressions for the same quantity x plus y plus z. So for instance, if we multiply this first row by this column, we get x plus y plus z and it is equal to 1. Similarly, if we multiply this second row by this column, then we again get x plus y plus z, but this time x plus y plus z will be equal to minus 1. So now we have the same quantity x plus y plus z equal to plus 1 and minus 1, but this cannot be simultaneously true, and so we say that only one of these can be correct. Now note that because this simultaneously cannot be true, we will discard x is equal to 1 as one of the solutions. So x is equal to 1 is not a solution in this case. So we will write, or rather alpha is not equal to 1. So in this case, alpha equal to 1 is not a valid solution, and so the only solution that is possible is alpha is equal to minus 1 as per this result. Now that we have discarded alpha equals 0 and taken alpha is equal to minus 1, the remaining question is very easy. The only thing we need to do is substitute the value of alpha as minus 1 in this equation, and so we get 1 plus alpha square in this case will be equal to 1 plus, now alpha is minus 1, and so alpha square will be minus 1 the whole square, which gives us the value 1 itself. So we finally obtained that the value of 1 plus alpha square is equal to 1 for this given condition, and so we will write the final value answer as the value of 1 plus, or rather I'll write it here separately, that the value of 1 plus alpha square is equal to 1. So this is the only possible value that this expression can take. So we've now seen how to solve this question related to matrices having or representing a system of infinite solutions.